So welcome everyone to the 6th lecture of the Reading Groupoid. And today is with us Paula Alba from UNED, and she's going to talk about action.
Thank you, Manolo, for the presentation. Today the lecture is about the actions. We are going to follow the sixth section of the first chapter of Mackenzie. Before showing the definition of an action of the groupoid over a manifold, let's think about reasonable expectations. If we wanna explode the structure of a groupoid, then every element of the groupoid is gonna be able to act on any element of the manifold. And if we wanna have the property that if two elements of the groupoid are composable, then the action of the composed element with an element of the manifold to be equal to H acting on Gm, then if a pair of elements of the groupoid are composable, we have to get that H can act on the action of G on any element of the manifold. So, with this in mind, the definition is: if we have a Lie groupoid over a manifold M, and we have a map, a smooth map F between another manifold and the base manifold, then the pairs that are going to be able to act on each other are what we will note as G star N prime, and it's going to be the fiber product of source map and F. And an action is going to be a map, a smooth map, that takes pairs of elements of G star N prime and takes them to N prime. And we are going to note, as in the action of a Lie groupoid, the action as the concatenation of the two elements. But this action, in order to respect the structure of the groupoid, we have to impose some properties. The first one is that F of Gm prime is the target of G. This is in order to get what we previously mentioned, that if H is composable with G, then the source of H is the target of G, and it's equal to F of G N prime. So we are going to be able to H is going to be able to act on G N prime. So if we have H that is composable with G and a pair of G star N prime, then we impose simply that the multiplication of H with M is equal to this thing. And also another property is that the units of the groupoid don't do anything on the elements of n prime. So since the elements, the units we will be able to act on n prime are going to be those which source and target is the same one as the image of n prime, and this has to be n prime. So given this definition, there's another thing to consider, that is the orbits. The orbits of an element of n prime are going to be simply the result of the actions of the elements of the groupoid. Also, an important thing to think about is that we would like to not also be this map smooth, but also its restriction to the elements, the action of the elements of the groupoid where they can act. But in the general definition, we don't ask for that. So with the full generality of the definition, the fibers of n prime that are the preimages by F are not manifolds. So obviously the action map restricts to the fibers is not smooth. But what happens if we have an F that is a surjective submersion? Then the fibers are closed embedded manifolds, submanifolds of M prime. And we also get that these restrictions are diffeomorphisms. Okay, so if we have that the fibers are submanifolds and the maps are smooth, then for each F's in M, the isotropy groups act on the fiber. And if with the smooth properties I mentioned is a E group action. So now some examples of this, so we can understand it. The first one is the trivial action. If we have any Lie groupoid and F any manifold, then we have an action of the groupoid on this Cartesian product that is defined as so this is the trivial action. It has no implication on the structure of the groupoid, neither on the manifold or on the structures we will see during the lecture. But what happens if we study a more complex or more interesting groupoids?
Sorry, maybe a question. I'm guessing like the F now is just the projection, no? Like n times F onto M, like the natural projection.
The F, yeah.
Okay.
I call the natural projection.
Okay.
Except two. Yes.
Thanks.
Now, we can define an action between the gates groupoid acting on its principal bundle. Because if we have the gauge groupoid and the principal bundle, here the pairs are the equivalent classes under the group. If we have this operation such that this P is the same as the projection of P2, then it has all the properties and F would be P. This is like considering the group action of the principal bundle, but in a little more tricky way, because this means that there exists G on the group such that this happens. Now, we talked a couple of lectures ago about the associated fiber bundle to an action of the group of a principal bundle on a manifold. So, if we have a principal bundle and an action of Y on a manifold F, we can consider the associated bundle, that is this one. So we can define an action of this groupoid, the gauge groupoid, on this fiber bundle just like this. And this is an action on P being P, the projection of the fiber bundle. Because if we consider the source of this pair, the source of this pair is the projection of P2. P2 is the projection of this pair on the fiber bundle, and the target of this pair is the projection of the principal bundle of P1. That is the projection. Yes. The target of this pair is this projection that is equal to this. So we have the properties we need. So on the lecture of the local triviality of Lie groups, Lie groupoids, we talked about the isomorphism between a locally trivial Lie group and a principal gauge groupoid. So one could wonder if the action of a locally trivial Lie groupoid is comparable or is isomorphic or something like that to the action of a gauge groupoid. In order to answer this question, we have to have tools to compare different actions of different groupoids over different manifolds. So the first step would be to consider the same groupoid acting on different manifolds. We have a Lie groupoid that acts on two manifolds on two different maps. Then we have a smooth map between the two different manifolds, and we would like for this map to respect the action between the action of the groupoid of the different manifolds. So if we have the base manifold of the groupoid and the two different manifolds, here we have this map and the F1 and F2. So we want this map to get fibers of this manifold, ascend them to fibers of this manifold. So we want this diagram to commute. So the first condition is going to be that F2 composed with phi is F1. But also we want this map to respect the action, like the action of the groupoid. So we have this action that takes elements of G star M1, two elements of M1, let's call it phi super 1, the map phi, and the other action on the other map. Then what happens if we consider ascending pairs of this manifold to pairs of this manifold? We have that we don't change the groupoid, so the element of the groupoid remains the same, and we change the second part of the pair. So since this diagram commute, this is this diagram commute, we have that we can multiply these pairs. So we want to ask that the action remains invariant. If a map between these manifolds has all these properties, we say that phi is the equivariance, the same way we did with group action. But what happens if we want to compare two different groupoids on different manifolds? And then we have two groupoids with two different actions, and let phi be a Lie groupoid morphism over F. If we want to construct a morphism that respects both actions, we have to have a map like this, because we are changing the manifold we act on and also the groupoid that acts. So we need a map that is equivariant. So we have this diagram, and we want it to commute. So the fibers remain with the same structure. So in this case, we have, I'm going to write on this diagram, we have the same thing as in here, but since we have two different groupoids, we have to have a key. Okay, so we want, we have this situation, and we want that the action on this side translates on the actions of on this side. So this translates to then if all these properties are true, then we say that this Lie group morphism is equivariant. So we have this tool to compare different Lie groupoid actions, and we want to apply it to the case we talked about locally trivial Lie groupoids. We prove that if G is locally trivial, is isomorphic to the gauge groupoid with BBN and source fiber, G the isotropic group for any X on the base manifold. So we have already seen that this groupoid acts on the fiber bundle associated to the action of the group on a manifold. So if there is the associated manifold that this group is going to act on, is going to be the fiber of the N prime. So theorem. If we call phi this isomorphism, and we call the same thing with the other, there exists a fiber bundle isomorphism between this and this, and this diffeomorphism is equivariant with respect to the isomorphism, the Lie group isomorphism we talked about. Considering that it goes from here to here. So this theorem tells us that every action of a locally trivial Lie groupoid is gonna act like this action we talked about in the examples. The proof it's really simple. The only tricky part is to see that there is such a fiber bundle diffeomorphism. But to clarify the concepts and the operations, the isomorphism that is from the gauge groupoid such this to the Lie groupoid is taking this to this, and the fiber bundle diffeomorphism since this fiber, this manifold was the fiber of M prime, we can act, G can act on A through the action of the Lie groupoid with N prime. I don't know if I wrote that, no. So these two morphisms are equivariant because if we take these pairs and this is the same as this. So it only would remain to prove that this is a fiber bundle diffeomorphism. That is, you can do it with the decomposition section, and I think it's not really important for me to show it because it's really similar to other examples. But what happens if
Sorry, are we assuming that df defines a fiber bundle? Like the m prime over m?
Yeah.
Okay.
Yeah, because if not, it doesn't make sense.
Okay.
Yes, sorry.
Thanks.
Now, what happens if we have a principal bundle and we want to make a relation between this action, the action of the gauge groupoid, with the associated fiber bundle to an action of the group over a manifold, and the same thing but with the action of the group over a different manifold. So we have two different action of the group on different manifolds, and we want to relate morphisms between this manifold that are equivariant with the action of the group, to morphisms that are equivariant under the action of the Lie groupoids. And it turns out that is quite nice, because if we have a is a G equivariant map, we can construct a map between the fiber bundles taking this. and this is a equivariant map. So as in the first definition about equivariant maps, in this case we are changing the manifold on where the Lie groupoid acts, so the action, the groupoid action remains the same. But we can also get the converse. So there is an equivalence between the different maps of this type of action. Okay, some more examples. The inner automorphism. If we have a locally trivial Lie groupoid, then we can define an action of G over its inner Lie groupoid taking any pair due to the theorem about the actions of locally trivial Lie groupoids, we have that and it was because of the theorem we talked about. Okay, so now, when we had a group action on a manifold, we could define a groupoid that was the groupoid of the action. So now, what is the, can we define an algebraic structure that conveys the action of the Lie groupoid? In terms of that, yes, and the algebraic structure is also a Lie groupoid, the Lie group action, the Lie groupoid of the action. So, if we have a Lie groupoid action, we can define the source being this map, the target being this one, and the inclusion, and multiplication. I'm writing it with prime to differentiate it to the structure maps of the groupoid G, because we are going to construct a different Lie groupoid that will be the action Lie groupoid. And the inversion pretty similar to the action groupoid of the action of a group. But if we this is the the action groupoid that is a groupoid that has as the space of arrows this manifold, and the base manifold is n prime, and the same way as with the groups, it's going to notice by and is the action associated to the action of the groupoid. So we can make a relation between this groupoid and the original groupoid. That is going to be very interesting when we define the intrinsic way to define the action of a Lie groupoid. We have this Lie groupoid, and we want to have a Lie group morphism to this groupoid. So if we project on the first component and we make the relationship with F, then this is a Lie group morphisms that is going to be very interesting. We study the intrinsic definition of the action of a Lie groupoid. So, for example, if we have a groupoid, this groupoid can act on itself by composing arrows. So what's the relationship between the groupoid and the groupoid action of the action of this groupoid acting on itself? No. Tongue twister. How will be the phrase? The action groupoid of a group of the action of the groupoid on itself. If we have this Lie groupoid, then the set of composable arrows will be the set of pairs that can act on each other. So we have this action, and if we define the action groupoid of this action, then the target is this one, and the source is this one. So we can take this Lie groupoid to this fiber product, that is the pairs that has the same target. That is simply taking the anchor of the group. Since this is a subgroupoid of the trivial groupoid, this has a structure of a groupoid, and this source and target have the property that if we take the anchor of the anchor, the other anchor, then this is the same. And this is a isomorphism between these Lie groupoids. It's a remark. For every, if we have a Lie groupoid over a point, then a Lie group, the action, the Lie group action, or action Lie groupoid, and is defined the same way, taking over itself. Taking translations, we can define an action, and the Lie group associated with that action is has the Lie group action Lie Groupoid itself is morphic to the pair groupoid. Super basic, but interesting. Now, I said that we can define a Lie groupoid action intrinsically. What I mean by that is that I'm going to define a type of Lie group morphism that defines an action of the group of one group to another. Let with different base manifold this is always a manifold, so we can define this map and we want to provide an action that goes from this manifold to n prime. So then if we get that, we are defining an action without going from there, going from the Lie group morphism. Set to be an action morphism. Okay, so we can wonder if we have a Lie group action, can we define an action morphism which will then evolve to the same action? We had this canonical Lie group morphism between the Lie group, the action Lie Groupoid, and the Lie groupoid. So having this morphism, we can define an action morphism from this morphism. Okay. I don't know if I have write it well, but the action morphism is actually phi. The imposed condition is over phi prime, but the action morphism is phi. An action. Since this being an action morphism implies that phi prime is a diffeomorphism, we can consider the inverse of phi prime. Then we have that going from this to this, if we compose the map, the inverse of phi prime, that takes elements of the fiber product into the first groupoid, and then the target of the first groupoid, then we end up in M prime, and this defines an action. I think there's no time for the proof, but the idea is that if we restrict this map to the fibers, the source fibers, then since this is a diffeomorphism, this implies that restriction is bijective. So we can take we can act we can have the properties of the action. So we want to guess if this the action that we construct here is the inverse of the process going from an action morphism to an action is the inverse of the process of having an action and then defining the action morphism that is the actual canonical morphism. It turns out that it is so we have that the first Lie groupoid on the morphism is isomorphic to the action Lie group morphism of the action that is associated to that action morphism. And also the opposite way, I have wrote what I said, that if we have if we begin from an action and construct the induced action morphism, that is the canonical morphism, this, because it's an action morphism, induced an action, and this action is the original one. And now the last part is we want to relate different actions by this type of morphisms. So it's not really canonical to write this, but it's the way Mackenzie does. We know a morphism of actions over G is a Lie groupoid morphism such that so now we are going to compare the action that the different action morphisms define by this type of morphism. So the same way we did with the intrinsic definition, we're going to think about what happens if we begin with a natural groupoid action. If is equivariant map of two actions we consider two actions with the same Lie groupoid because when we defined the action of this Lie groupoid over this manifold, the Lie group that was actually acting was the second one. So if we have a groupoid morphism of action, then the groupoid that remains the same is the second one. So the one that is going to act is the same one on both sides. So we can define this map is a morphism of actions. And we want to do the converse. If a morphism of actions is defined between two action morphisms, then what happens to the groupoid actions they defined? Since a morphism of action is a Lie group morphism, it has a map between the base manifolds. I'm going to talk that phi sub naught with respect to the attributes So this morphism of actions take one action induced by the action morphism to the other, and it preserves the properties. So what does it mean? That the category of actions morphisms over this Groupoid is equivalent to the category of actions of Y and the variant maps. Because if we have two actions and an equivariant map, we are in this scenario. So we constructed the action morphism, and if we have an action morphism of over a fixed Lie groupoid, we are on this case, and we constructed we stated that there is an equivariant map between the two actions of the groupoid. A simple but very useful property about morphisms of actions is morphisms of actions or action morphisms propositions is that given an action morphism and morphism of Lie groups, groupoids, that doesn't have to be an action morphism. The composed map is an action morphism if and only if the second one is. But what's the purpose of constructing the action groupoid is that we can deduce properties of the action by having properties of the action groupoid. So if we have an action that is transitive this is equivalent to the action groupoid being transitive. And also the action is free if only if the free image of the anchor on the diagonal is only the unity. It would be better to take primes because it's the anchor of the action groupoid. So and to end up with this lecture, what happens, this is without imposing any property on the map F, and we saw that the map F don't has any extremely good properties. So what happens if we have an action with F being a surjective submersion, then the action groupoid being transitive not only the original groupoid also is transitive, but some and hence every vertex groupoid or isotropy groupoid acts on the fibers on the fibers transitively, or however it is spelled, transitivity.
Sensitively, porque sí están, no sé, pero.
For example. Also, if also considering that F is a surjective submersion, if the action groupoid is locally trivial, also without the if only if the original groupoid is locally trivial, and some and hence every restriction map. Also called restriction or evaluation map. Is also a surjective submersion. And that's it. I hope you enjoyed it.
Okay. Thank you. Well, so thank you, Paula, for the lecture. Does anyone have any question?
Yeah. Could you please maybe provide some example of action groupoid not coming from a Lie group action? And maybe also some example about morphism of actions.
You said an action.
An action groupoid, right?
Yeah.
Which does not come from a Lie group action, which is not a transformation groupoid.
I don't know if it is possible.
For sure. I think, I mean, if not, it would be like action groupoids are only coming from Lie groups, right? And I was
okay.
asking
so
for
you meant not coming from a group action.
Yeah.
Okay. The action of the gauge groupoid doesn't come
Yeah, but
from.
maybe one different or a particular case, just to see like a very concrete example of
Yeah,
how
I
it
think
works.
I have one. What is the trivial groupoid? That is not very complex. Yeah, I think I don't have any. Maybe the automorphism action, the inner automorphism action, because both of them are Lie groupoids. That's the only thing I have.
Are there any more questions? Remarks?
Okay, so thank you again, Paula, for the lecture.
Maybe we have some important.
Yeah, then next week we have the lecture given by Thomas in Warsaw. So we will see the lecture together here in Madrid.
Yeah, also, like just to mention that there are 2 more spots left after Thomas.
Okay, you want to see?
Just
so please be brave and
yeah.
we don't want to have all the fun. You can also have the part of the fun of giving a lecture.
I don't think there are a lot of people. I don't think there are a lot of people today, but just in case anyone sees the recording, I'm gonna maybe what can I erase? Maybe this part is the
oldest one.
This is the oldest, no?
I think
Yeah.
so.
I mean, this is kind of superfluous information for the people that are present here, but whatever. So after the next session, which will be given by Thomas, which is on what day? First of the second, no? The second.
Yeah,
Second.
The 2nd of December will be with Thomas. And then we have 2 more sessions left on the 9th and on the 16th, which we sort of estimate or we would like to cover sections 2.3 and 2.4 of the book of Mackenzie's. This on the 9th, and on the 16th, 2.4 like ending, and 2.5. This would be like the idea, not to give a lot of detail on chapter 2 because there are a lot of messy.
The camera doesn't follow you.
Sorry.
Maybe.
Okay. So on the 9th, like to cover somewhat 2.3 and 2.4, and the 16th to cover somewhat whatever was missing of 2.4, and if we can, whatever is missing of the section 2.5. Not giving a lot of technical
For sure.
details.
And maybe like trying to focus more on maybe examples. Like, I don't know. It depends on what the speaker wants. Sure, but I mean, maybe it will be. I don't know what you.
Yeah, more just to give definitions and some examples, and that's it.
Yeah, more practical.
Yes, and just to more or less end with start with algebroids on the first.
Yeah.
On the start of the next semester. Probably there will be some parts left to cover on the first 2 lectures, but okay. This is somewhat the schedule. But we are missing 2 speakers, so if anyone, I know
So
the people that are present already have spoken.
Yeah.
But
So in case maybe we have to repeat again.
yeah, it's okay. Does anyone want to say anything more?
I don't think so. I think you said basically what we wanted to mention.
Okay.
Okay.
So that's it.
So that's it. Next week we have theory and applications.
The trailer groupoid.
See you
Well, so see you next week then.
Yeah, see you next
See you
week.
guys.